Tonight, a simple question reveals one of the strangest mysteries in the universe. Every planet spins, moons spin, stars spin, even entire galaxies slowly turn through space. But if everything spins, why does every world spin differently? Why does Earth take 24 hours to rotate while Jupiter completes a day in less than 10? Why does Venus spin backward? Why does Uranus appear to roll through space on its side? And why do some worlds seem to defy the rules that shape the rest of the solar system? Over the next journey, this video explores the hidden forces that set entire planets in motion, the ancient collisions that change their destinies forever, and the surprising reason spin may be one of the most important properties in the universe. If this is the kind of cosmic mystery that sparks curiosity, please take a moment to like the video and subscribe to Cosmic Bedtime Stories. Every subscription helps bring more relaxing science journeys and deep space adventures to the channel. Now, as the universe slowly turns around us, it is time to discover why every planet spins differently. In the outer regions of space, motion is present long before any star or planet exists. Vast clouds of hydrogen and helium drift through the galaxy, spread across distances so large that density becomes extremely low, yet not entirely uniform. Within these clouds, every small variation in density carries a trace of motion inherited from earlier cosmic events. This motion is not organized into clear rotation at first. It appears as slow drifting currents shaped by gravity radiation pressure and the residual turbulence of past stellar explosions. Over time, these motions begin to reveal a subtle pattern, a tendency for parts of the cloud to rotate, even if only faintly around invisible centers of mass. Angular momentum is the key physical principle that governs this behavior. Angular momentum is a measure of rotational motion that remains conserved unless acted on by an external torque. In interstellar space, there are almost no strong external torques, so even the smallest initial rotation of a gas cloud persists. When different parts of the cloud drift toward one another under gravity, they do not fall straight inward. Instead, they spiral slightly as they move, preserving the rotation already present. This slow spiraling is not dramatic, but across millions of years it becomes significant. As gravity gathers matter, the cloud begins to contract. The contraction is uneven because denser regions pull in surrounding material more strongly. Where collapse begins, rotation becomes more noticeable. The cloud does not spin like a solid object. Instead, different layers rotate at slightly different speeds. Outer regions move slowly while inner regions gradually accelerate. This difference in speed is a natural consequence of conservation of angular momentum. As the radius of rotation decreases, the rotational speed increases even if no new force is added. Turbulence inside the cloud adds further complexity. Small shock waves pass through the gas, often triggered by nearby supernova remnants or stellar winds from distant stars. These disturbances introduce local variations in motion. Some regions gain additional spin while others lose it or reverse direction slightly. Despite this complexity, the overall structure of rotation tends to persist because gravity continues to pull matter inward. Magnetic fields also play a subtle role in shaping motion. Although weak compared to gravitational forces on large scales, they can guide charged particles within the gas. This introduces slight alignment in movement along magnetic field lines. The result is not a uniform spin, but a layered and textured pattern of rotation that reflects both internal and external influences. As the cloud continues to evolve, small regions begin to separate from the larger structure. These denser pockets of gas mark the early stages of star formation. Each pocket inherits a portion of the cloud's overall angular momentum. The direction and speed of their rotation depend on the local balance of forces at the moment of collapse. No two regions behave exactly the same way even within the same cloud. At this stage, rotation is still diffuse and unorganized. but it carries forward the essential property that will shape all future structures formed from this material. Every planet, every star, and every system of orbiting bodies begins with this faint inherited spin embedded in interstellar matter. It is not created anew at each stage, but preserved and redistributed as gravity reshapes the cloud. The outermost regions of space remain the quiet foundation of this process. Even where matter is sparse, motion continues in subtle forms. Over long timescales, these motions accumulate into structured rotation, preparing the conditions for more defined cosmic systems to emerge. Within the most tenuous edges of these clouds, where particles are separated by vast distances, motion becomes almost imperceptible. Yet even here, statistical patterns of drift can be measured indirectly through spectral shifts in light from background sources. These measurements show that gas does not remain completely static, but participates in slow collective flows shaped by the gravitational field of the galaxy as a whole. These flows contribute to the initial seeds of rotation that later grow into more coherent structures. The preservation of spin across scales depends on the isolation of these regions from disruptive forces. In areas far from active star formation, angular momentum is rarely exchanged with external systems. This allows initial rotational bias, however small, to remain embedded in the cloud for extremely long periods. As gravitational contraction continues, these biases become amplified, turning nearly uniform gas distributions into rotating protostructures with increasingly defined axes. In some cases, neighboring clouds interact weakly through tidal gravitational forces. These interactions do not destroy rotation, but they can slightly reshape it, tilting or stretching the distribution of motion. Over time, such interactions introduce subtle diversity in rotational orientation across different regions of a galaxy. This diversity is one reason why later planetary systems do not share identical spin directions. As contraction progresses further, the internal energy of the gas increases due to compression. Collisions between particles become more frequent, redistributing energy and smoothing out extreme variations in local motion. Despite this smoothing effect, the overall angular momentum remains conserved, ensuring that the global rotational trend persists, even as local turbulence evolves. Eventually, the cloud reaches a state where gravity dominates over most other influences, and rotation becomes a defining characteristic of its structure. This marks the transition toward more organized systems, where spin is no longer a faint background feature, but a central property shaping all subsequent formation processes. At this deeper stage, rotation begins to influence how matter distributes itself within the collapsing region. Material moving inward tends to avoid direct radial paths, and instead follows curved trajectories shaped by the existing spin. This curvature leads to the gradual formation of flattened structures even before any star ignites. The system naturally organizes into a disk-like arrangement, where most motion occurs within a shared plane defined by the conservation of angular momentum. This plane becomes increasingly stable as collisions between particles dissipate irregular motion. The emerging structure is still diffuse and dark, but its internal dynamics are already structured by rotation. Over extended time, this early organization determines the alignment of all later bodies formed from the same cloud, embedding a directional consistency that persists through every subsequent stage of planetary system development across vast cosmic timescales unfolding slowly. Within the same vast interstellar environment, molecular clouds begin their inward collapse under the persistent influence of gravity. These clouds are colder and denser than their surroundings, composed primarily of molecular hydrogen, mixed with traces of helium and heavier elements produced by earlier generations of stars. At low temperatures, thermal pressure is weak, so gravity slowly gains dominance over internal gas support. This balance between outward pressure and inward pull defines the earlier stage of collapse, where structure begins to shift from diffuse distribution into concentrated regions of matter. As the cloud contracts, small fluctuations in density become increasingly important. Regions that are slightly denser than their surroundings attract more material, strengthening their gravitational pull. This process is gradual but self-reinforcing. Each small accumulation of mass increases local gravity, which draws in more gas, further increasing density. Over long periods, this feedback mechanism transforms a nearly uniform cloud into a collection of uneven, evolving structures. The collapse is not instantaneous, but occurs across extended spans of time measured in hundreds of thousands to millions of years. Temperature plays a critical role in regulating this process. As gas particles fall inward, gravitational potential energy is converted into kinetic energy, increasing particle motion and raising temperature. However, molecular clouds can radiate energy efficiently through infrared emission, allowing them to cool despite compression. This cooling prevents pressure from rising too quickly, enabling collapse to continue. Without this radiative cooling, the cloud would resist contraction more strongly and remain more diffuse. During collapse, angular momentum becomes increasingly significant. Even a slow initial rotation of the cloud becomes amplified as the radius of contraction decreases. The conservation of angular momentum ensures that as material moves closer to the center of mass, its rotational speed increases. This does not create new motion, but concentrates existing motion into smaller spatial regions. The result is a gradual increase in rotational differentiation, where inner regions begin to move faster than outer layers. As collapse continues, the cloud does not fall inward uniformly. Instead, material follows curved trajectories influenced by both gravity and rotation. This curvature introduces a natural flattening tendency, although full disk formation has not yet fully stabilized. Instead, the cloud develops elongated structures and irregular flows that reflect the competing influences of gravity pressure gradients and rotational forces. These structures are dynamic, constantly reshaping. As material moves inward and energy is redistributed through collisions between particles, magnetic fields embedded in the interstellar medium add further complexity. Charged particles within the cloud interact weakly with these fields, which can guide the flow of gas along preferred directions. This introduces anisotropy into the collapse, meaning that contraction does not proceed equally in all directions. Instead, certain pathways of motion become more favorable, subtly shaping the geometry of the collapsing region. Although magnetic forces are not dominant compared to gravity, their influence becomes noticeable in regulating fine-scale structure. As density increases, the cloud becomes increasingly opaque to its own radiation. Energy generated by compression becomes trapped more effectively, slowing, cooling in the densest regions. This leads to temperature gradients within the collapsing cloud, where outer regions remain relatively cool, while inner regions gradually warm. These gradients affect pressure distribution and contribute to variations in collapse speed across different zones of the cloud. Fragmentation begins to emerge as a natural outcome of these conditions. When certain regions become sufficiently dense, they decouple from the surrounding material and begin collapsing independently. This fragmentation is driven by gravitational instability, where local regions exceed a critical density threshold and collapse faster than their surroundings. Each fragment inherits its own motion, rotation, and density profile, leading to multiple centers of collapse, forming within the same original cloud. Within these fragments, motion becomes more organized. The combination of gravity and rotation leads to the concentration of material towards central axes, while outer regions continue to supply mass inward. Collisions between particles within these fragments convert kinetic energy into heat, but efficient cooling mechanisms allow collapse to proceed further. Over time, these fragments evolve into distinct protostructures, each developing its own internal dynamics. The conservation of angular momentum continues to shape the evolving structure of each fragment. As collapse proceeds, rotational speed increases but not uniformly. Variations in initial density and motion produce differences in rotational behavior across fragments. Some rotate more rapidly, while others exhibit slower or more irregular motion. These differences will later influence the characteristics of any systems formed within them. Gravitational forces dominate all other interactions at this stage, but they act within a complex environment shaped by pressure, temperature, magnetic influence, and residual turbulence. The interplay of these factors ensures that collapse is not smooth or uniform, but instead highly structured and dynamic. Small perturbations grow over time, producing increasingly complex internal patterns. As fragments continue to contract, their internal densities rise significantly. The material becomes increasingly compressed towards central regions, while outer layers remain more diffuse. This radial gradient of density sets the foundation for future structural differentiation. Although no distinct stellar core has yet formed, the conditions necessary for such development are gradually being established. Throughout this process, motion remains continuous and interconnected. Gas flows inward along curved paths influenced by both global collapse and local variations in structure. Energy is redistributed constantly through collisions and radiative processes, maintaining a dynamic balance between contraction and resistance. The system remains far from equilibrium, with every region participating in ongoing transformation. Eventually, the collapsing fragments reach a stage where their internal structure becomes sufficiently distinct from the surrounding cloud. At this point, they begin to behave as semi-independent systems, each continuing its inward evolution under its own gravitational influence. These regions represent the transition from large-scale cloud dynamics to localized structures that will later develop into more defined astronomical bodies. The collapse phase therefore serves as the bridge between diffuse interstellar matter and the organized rotational systems that emerge in later stages of formation. Within the collapsing fragments of molecular clouds, matter begins to settle into increasingly organized structures, driven by the continuous pull of gravity and the persistent conservation of angular momentum. As density rises, the motion of gas no longer appears random at large scales. Instead, it gradually aligns into a coherent pattern of rotation centered around forming gravitational cores. These cores are not yet stars, but they mark the beginning of a structured system where inward collapse and rotational balance shape the geometry of all surrounding material. As the fragment contracts further, the rotation inherited from the parent cloud becomes more pronounced. The reduction in radius causes an increase in rotational speed, not because new energy is added, but because angular momentum is preserved. This intensification of spin leads to a strong directional bias in the motion of infalling gas. Material moving toward the center cannot fall directly inward due to rotational resistance. Instead, it spreads outward into a flattened configuration, forming what is known as a protostellar disk. This disk is a transitional structure, still evolving and unstable, yet already defining the future architecture of planetary systems. The disk is composed of gas and dust that orbit the central protostar. The gas remains largely molecular hydrogen with helium, while dust grains contain heavier elements such as carbon, oxygen, silicon, and iron. These solid particles interact through collisions, sticking together when conditions allow. The disk is not uniform. Its density and temperature vary with distance from the center, creating distinct zones where physical processes differ significantly. Inner regions are hotter and more energetic, while outer regions remain colder and more stable. Within this, rotating disk motion is governed by a balance between gravity pulling material inward and centrifugal effects arising from rotation. This balance does not create a static system, but a dynamic equilibrium where material continuously moves while maintaining overall structure. Gas flows inward along spiral paths, gradually feeding the central protostar. At the same time, some material is redistributed outward through interactions and collisions, creating complex circulation patterns within the disk. Dust grains play a crucial role in shaping the early structure of the disk. These microscopic particles collide frequently due to their relative motion within the gas. At low velocities, collisions allow grains to stick together through electrostatic and van der Waals forces. Over time, these small aggregates grow into larger clumps. This process, known as accretion, is gradual and uneven, influenced by local density variations and turbulence within the disk. The growth of these solid bodies marks the first step toward planet formation. Turbulence within the disk introduces variability into the otherwise structured flow of material. Small-scale eddies and vortices form as gas moves through regions of differing density and temperature. These turbulent motions can either enhance or inhibit the growth of dust aggregates depending on local conditions. In some regions, turbulence concentrates material, accelerating growth. In others, it disrupts forming structures, breaking them apart and redistributing particles. Temperature gradients within the disk are particularly important in determining its chemical and physical evolution. Near the central protostar, temperatures are high enough to vaporize many solid compounds, leaving only refractory materials capable of withstanding intense heat. Farther away, temperatures drop sufficiently for volatile compounds such as water, ammonia, and methane to exist in solid form as ice. These differences create distinct compositional zones within the disk, influencing the types of bodies that will eventually form. Magnetic fields remain present within the disk, interacting with ionized gas and influencing its motion. Although the gas is mostly neutral, even a small fraction of ionized particles can couple with magnetic field lines. This coupling affects angular momentum transport, allowing material to move inward more efficiently in some regions while slowing it in others. This process contributes to the gradual evolution of the disk's structure over time. As material continues to accrete onto the central protostar, the protostar itself grows in mass and temperature. Gravitational energy released during accretion heats the core, causing it to emit increasing amounts of radiation. This radiation begins to influence the surrounding disk, driving slow changes in temperature and chemistry. However, nuclear fusion has not yet become fully sustained. The object remains in a transitional state dependent on continued accretion for its energy output. The disk gradually evolves as regions of enhanced density begin to form. These regions arise from local gravitational instabilities, where small variations in mass distribution lead to stronger inward attraction. Over time, these dense regions grow, separating from the surrounding material and becoming distinct bodies within the disk. These early structures represent the initial stages of planetesimal formation. As rotation continues to shape the system, the distribution of angular momentum becomes increasingly uneven. The inner regions lose angular momentum more rapidly, as material accretes onto the central protostar, while outer regions retain higher rotational energy. This redistribution is mediated by gravitational interactions, turbulence, and magnetic effects. The result is a slowly evolving disk where material constantly shifts between inward and outward motion, while maintaining overall rotational coherence. The protostellar disk thus represents a critical stage in the transformation from diffuse interstellar matter into structured planetary systems. It is within this environment that the fundamental differences in planetary spin begin to take shape. Variations in local density, temperature, and angular momentum distribution ensure that no two forming regions evolve identically. Each future planet inherits a unique rotational signature determined by the complex dynamics of this early disk phase. As the system continues to evolve, the central protostar grows more stable, while the surrounding disk becomes increasingly structured. Material within the disk continues to interact, collide, and coalesce, setting the foundation for the formation of larger bodies. The balance between gravity, rotation, turbulence, and radiation defines every aspect of this environment, ensuring that motion remains dynamic and continuously evolving across all spatial scales within the system. Within the evolving protostellar disk, dust grains become the primary building blocks of larger structures, and their behavior begins to define the early architecture of future planetary systems. These grains are extremely small, often composed of silicates, carbon-rich compounds, and metallic elements formed in earlier stellar environments. In the cold outer regions of the disk, they remain stable and solid, drifting slowly through gas that moves in organized but constantly shifting flows. Their motion is influenced by drag forces which arise from interactions with surrounding gas particles. This drag gradually reduces relative speeds between dust and gas, allowing grains to settle toward the midplane of the disk. The midplane is the densest region of the disk, where gravity, rotation, and pressure converge into a thin layer of concentrated material. As dust settles into this plane, collisions become more frequent. These collisions are gentle at first, allowing particles to stick together rather than break apart. Electrostatic attraction plays an important role at this scale, as microscopic charges on grain surfaces help bind them during low-speed encounters. Over time, this process leads to the formation of increasingly complex aggregates, where clusters of particles grow into porous, irregular structures. As these aggregates increase in size, their interaction with the surrounding gas changes. Larger particles experience less drag relative to their mass, allowing them to decouple partially from gas motion. This decoupling introduces differences in orbital speed between gas and solid material, leading to further collisions and growth opportunities. In regions of higher density, growth accelerates, while in more diffuse regions, particles remain small and widely dispersed. Turbulent motion within the disk continues to influence this growth process. Small-scale eddies create localized zones of pressure variation, which can trap dust particles temporarily. These pressure traps increase the likelihood of collision and aggregation, allowing certain regions to become centers of enhanced growth. However, turbulence is not uniformly beneficial. In some areas, it introduces destructive relative velocities that prevent grains from sticking, breaking apart fragile aggregates and redistributing their components. As dust aggregates grow beyond millimeter and centimeter scales, their internal structure begins to change. They become less like collections of individual grains and more like loosely bound bodies with internal porosity. This porosity affects their mechanical strength and their interaction with gas flow. Larger aggregates begin to settle more efficiently toward the midplane, reinforcing the layered structure of the disk and increasing local density further. Temperature variations across the disk play a significant role in determining the composition of growing aggregates. In the inner disk, high temperatures prevent volatile compounds from condensing, limiting solid material to refractory substances that can withstand intense heat. In contrast, the outer disk allows the formation of ice, including water, ice ammonia ice, and methane ice. These ices significantly increase the available solid mass, accelerating growth processes in colder regions and contributing to differences in eventual planetary composition. As aggregates grow, gravitational attraction between them becomes increasingly relevant. Once bodies reach sizes on the order of kilometers, self-gravity begins to dominate their internal cohesion. These larger bodies are no longer governed primarily by surface forces, but instead by their own gravitational pull. This transition marks the formation of planetesimals, which are the first solid bodies capable of significantly influencing their surroundings through gravity. Planetesimals interact with each other through collisions and gravitational encounters. Some collisions result in accretion, where bodies merge to form larger objects. Others result in fragmentation, where impacts break bodies apart into smaller pieces. The balance between these two outcomes depends on collision velocity composition and structural integrity. Over time, accretion dominates in regions where conditions are stable, allowing larger bodies to emerge. The distribution of planetesimals within the disk is not uniform. Certain regions become densely populated with growing bodies, while others remain relatively sparse. This uneven distribution is influenced by variations in gas pressure temperature gradients and the initial density structure inherited from earlier stages of collapse. These variations ensure that planetary formation proceeds differently in different regions of the disk, even within the same system. Angular momentum continues to play a defining role in shaping motion at this stage. As material is incorporated into growing bodies, the distribution of rotational energy changes. Some planetesimals acquire significant spin due to asymmetrical accretion and off-center collisions. Others remain slower rotating depending on their growth history and local environment. These differences in spin begin to establish the diversity of rotational states that will characterize mature planets. Gas within the disk continues to exert a damping effect on the motion of solid bodies. This interaction, known as gas drag, gradually modifies the orbits of planetesimals, causing them to migrate inward or outward, depending on their size and local conditions. This migration influences where collisions occur and how material is redistributed throughout the disk. Over long periods, gas drag contributes to the convergence of material into preferred regions of accumulation. Magnetic fields remain weak but still present, interacting primarily with ionized gas components. These fields influence angular momentum transport, allowing some regions of the disk to lose rotational energy more efficiently than others. This process contributes to the gradual inward flow of material toward the central protostar while also shaping the outer disk structure. As planetesimals continue to grow and interact, the early foundation of planetary systems becomes increasingly defined. Each body carries a unique combination of mass composition and rotational motion inherited from its local environment. These characteristics are not random, but emerge from the complex interplay of physical forces operating throughout the disk. The system remains dynamic and evolving with continuous feedback between growth motion and environmental conditions. Dust gas and growing solid bodies all interact within a structured yet constantly changing environment. Over time, this interaction leads to the emergence of larger planetary embryos, setting the stage for the next phase of development, where gravitational dominance becomes even more pronounced, and the architecture of planetary systems begins to take its final shape. Within the protoplanetary disk, planetesimals begin to transition into larger planetary embryos through repeated accretion and gravitational interaction. These bodies are no longer small aggregates of dust and ice, but increasingly massive objects capable of shaping their local environment. As their mass increases, their gravitational influence extends farther into surrounding space, drawing in nearby material and altering the motion of neighboring bodies. This stage marks a shift from passive accumulation to active gravitational dominance, where growing embryos begin to compete for available material within the disk. The process of accretion becomes more complex as bodies grow larger. Collisions between planetesimals are no longer gentle or uniformly constructive. Instead, they vary widely in outcome depending on impact angle, velocity, and composition. Some collisions result in perfect mergers where two bodies combine into a single larger object. Others are partial stripping outer layers, or redistributing material without full integration. In high-energy impacts, fragmentation occurs, producing debris that may later reaccrete or be lost from the local region. This variability creates a dynamic environment where growth is uneven and episodic rather than steady. Gravitational focusing becomes increasingly important at this scale. Larger bodies enhance their effective cross-section by bending the trajectories of nearby objects toward them. This effect increases the likelihood of collision beyond simple geometric probability. As a result, the largest embryos tend to grow faster than smaller neighbors, creating a natural hierarchy of mass distribution within the disk. Over time, this leads to a few dominant bodies surrounded by a diminishing population of smaller remnants. Rotation begins to play a more visible role in the structure of these growing embryos. As material accretes asymmetrically, angular momentum is transferred unevenly, causing bodies to spin. Impacts that strike off-center contribute additional rotational energy, sometimes significantly altering spin rates or even reversing rotation direction. Each collision carries its own angular momentum signature, and the cumulative effect of many such events determines the final spin state of each emerging planet. At the same time, the surrounding gas continues to interact with these growing bodies. Gas drag gradually modifies their orbits, causing slow inward or outward migration depending on local conditions. This migration influences where embryos accumulate and collide. In some regions, bodies drift closer together, increasing the likelihood of large-scale impacts. In others, they are dispersed, reducing interaction rates and slowing growth. The interplay between migration and accretion creates a constantly shifting spatial distribution of material. Thermal conditions within the disk remain highly variable. In inner regions, high temperatures cause partial melting of solid materials during large impacts. This melting allows for differentiation processes to begin within growing embryos. Dense materials such as iron and nickel begin to sink toward the center, while lighter silicates remain closer to the surface. This internal structuring marks the beginning of layered planetary composition, where distinct core and mantle regions emerge over time. In outer regions of the disk, lower temperatures allow volatile compounds to remain stable. Ice-rich embryos form more easily in these zones due to the increased availability of solid material. These bodies tend to grow more massive as ice contributes additional mass that is unavailable in warmer regions. The presence of ice also affects the physical behavior of collisions, often making impacts more dissipative and increasing the likelihood of accretion rather than fragmentation. Turbulence within the disk continues to influence the growth process, though its role becomes more indirect at this stage. Large-scale turbulent structures can alter the distribution of gas pressure, creating regions where migration slows or accelerates. These pressure variations can trap growing embryos, temporarily increasing the likelihood of repeated interactions within localized zones. However, as bodies grow more massive, they become less responsive to small-scale turbulence and more dominated by gravitational interactions. Magnetic effects remain present but secondary compared to gravitational forces. They continue to influence gas dynamics, which in turn affects migration patterns of solid bodies. The coupling between ionized gas and magnetic fields helps regulate angular momentum transport within the disk, slowly reshaping its overall structure and influencing long-term evolution. As embryos grow larger, their gravitational fields begin to clear gaps in the surrounding disk material. This clearing process reduces local density, limiting further growth from nearby material and creating distinct orbital zones. These gaps mark the beginning of system organization, where space becomes divided into regions dominated by individual planetary bodies. The system transitions from a continuous disk into a structured set of interacting orbits. Collisional histories become increasingly important in determining final planetary characteristics. Each growing body carries a record of its past impacts encoded in its rotation, composition, and internal structure. Some bodies experience a few large transformative collisions, while others undergo many smaller accretion events. These differences lead to significant variation in final planetary properties even within the same system. Angular momentum redistribution remains a central process throughout this stage. As material is accreted or lost through collisions, the distribution of rotational energy across the system evolves continuously. Some bodies gain rapid rotation, while others slow down due to tidal interactions or loss of angular momentum during impacts. This diversity in rotational states begins to establish the wide range of spin behaviors observed in mature planets. The protoplanetary disk at this stage is no longer a uniform environment, but a structured system of interacting bodies embedded within residual gas. Growth continues, but increasingly under the influence of established gravitational hierarchies. Larger embryos dominate their regions, shaping the flow of material and influencing the evolution of smaller neighbors. The foundations of planetary systems are now clearly established, and the processes that determine final planetary spin are actively unfolding through continuous interaction between motion, mass, and gravity. Within the late protoplanetary disk, planetary embryos grow large enough to dominate their surrounding regions, and gravitational interactions become the primary driver of motion. The disk is no longer a uniform field of gas and small particles, but a structured environment where distinct bodies shape local dynamics. Each embryo exerts a gravitational pull that alters nearby orbits, clearing pathways and concentrating material into specific zones. These zones of influence define the early architecture of planetary systems, where spacing and interaction patterns begin to stabilize. As embryos increase in mass, their ability to accrete surrounding material becomes limited by local depletion. The region around each growing body gradually loses accessible solid matter, creating gaps in the disk. These gaps are not empty, but contain reduced densities of gas and dust insufficient to sustain rapid growth. This reduction forces embryos to interact more strongly with one another, rather than with dispersed material, shifting the dominant mechanism of evolution from accretion to gravitational dynamics. Orbital resonances begin to emerge as bodies interact through repeated gravitational influence. When orbital periods align in simple ratios such as 2:1 or 3:2 bodies exert periodic forces on each other. These repeated interactions can stabilize or destabilize orbits depending on their configuration. In some cases, resonance locks bodies into long-term stable patterns. In others, it increases orbital eccentricity, leading to more elongated paths and heightened collision risk. These resonances contribute significantly to the long-term structure of planetary systems. Collisions between large embryos are rare but highly energetic. When they occur, they can dramatically reshape both bodies involved. Material is redistributed, and in some cases entire mantles are stripped away or merged. These giant impacts are capable of altering rotational states significantly, sometimes resetting spin direction entirely, or producing extreme axial tilts. Each event becomes a defining moment in the evolutionary history of a planet, leaving long-lasting structural and rotational consequences. Rotation at this stage becomes increasingly complex. Bodies no longer spin solely as a result of gradual accretion, but also due to the cumulative effects of major impacts and gravitational interactions. Spin rates vary widely, and rotational axes may be significantly tilted relative to orbital planes. These variations arise naturally from the stochastic nature of collisions and the chaotic early environment of planetary formation. The residual gas in the disk continues to influence motion, though its density has decreased substantially. Gas drag now acts primarily on smaller bodies and fragments, while larger embryos are less affected. However, the remaining gas still plays a role in damping orbital eccentricities over long timescales, gradually circularizing orbits and contributing to system stability. This damping effect helps transition the system from a chaotic formation stage into a more ordered configuration. Thermal energy generated by large impacts contributes to internal differentiation within growing planets. As energy from collisions is absorbed, internal temperatures rise, allowing materials to partially melt or fully liquefy. This melting enables dense elements such as iron and nickel to sink toward the center, forming cores, while lighter silicates rise to form mantles and crusts. This separation of materials establishes long-term internal structure, which influences later thermal evolution and magnetic field generation. In outer regions of the system where temperatures remain low, icy bodies continue to accumulate material more efficiently. These bodies often grow larger due to the abundance of solid volatile compounds. Their composition leads to different structural and dynamical behavior compared to rocky planets. Ice-rich planets, or large icy moons, form in these regions, reflecting the strong influence of temperature gradients within the original disk. Magnetic fields generated by the central protostar and by ionized regions of the disk continue to shape gas dynamics. Although their influence weakens as gas density declines, they still contribute to angular momentum redistribution within remaining material. This slow transfer of momentum helps regulate the final stages of disk dissipation and influences how residual matter is incorporated into forming planets or expelled from the system. As the system evolves, gravitational interactions between embryos become more dominant than interactions with gas. These interactions include scattering events, orbital exchanges, and gradual migration caused by mutual gravitational perturbations. Over long timescales, these interactions lead to the clearing of unstable regions and the stabilization of remaining orbital configurations. Each growing planet carries a unique dynamical history shaped by its local environment. The distribution of mass, the timing of collisions, and the sequence of orbital interactions all contribute to its final properties. Rotation in particular emerges as a sensitive record of these early processes. Variations in spin, direction, speed, and axial tilt reflect the cumulative influence of accretion impacts and gravitational exchanges. By the end of this stage, the system is transitioning away from a disk-dominated structure toward a planet-dominated architecture. Residual gas continues to dissipate, and solid bodies become the primary agents of motion. The emerging planets now define the gravitational landscape shaping the final arrangement of the system. The diversity in planetary spin observed at this point is a direct consequence of the complex and often chaotic interactions that occurred during these formative stages, where every collision, migration, and resonance contributed to the final distribution of rotational motion. As the protoplanetary disk continues to dissipate, the environment becomes increasingly dominated by solid bodies rather than gas. The remaining gas is thin and uneven, no longer capable of strongly shaping orbital motion on a system-wide scale. Instead, gravitational interactions between emerging planets and large embryos define the final structure of the planetary system. The space between these bodies is still active, but motion is now primarily governed by mutual gravity rather than drag from a dense gaseous medium. In this evolving environment, orbital paths begin to stabilize into long-term configurations. Planets that have cleared their immediate surroundings maintain relatively stable orbits, while smaller remnants continue to drift, collide, or become ejected from the system entirely. These residual objects include leftover planetesimals, fragments from past collisions, and icy bodies that never fully accreted into larger planets. Their motion is increasingly chaotic, shaped by repeated gravitational encounters with larger bodies. planetary spacing becomes more defined as systems reach a state of partial equilibrium. Larger planets dominate distinct orbital zones while smaller bodies occupy transitional regions or remain in distant, loosely bound orbits. This spacing is not perfectly uniform, but reflects the outcome of many previous interactions, including migrations, resonances, and scattering events. Each system develops its own internal structure, but all share the same underlying principle. Gravity organizes matter into stable orbital hierarchies over time. As gas continues to dissipate, its role in damping orbital eccentricity diminishes. Planets that once had slightly elongated or tilted orbits retain those characteristics more permanently. Without significant gas resistance, orbital corrections occur only through gravitational interactions between bodies. These interactions are less efficient at smoothing motion, meaning that early dynamical history becomes preserved in orbital architecture. The final stages of accretion are dominated by late impacts between large bodies. These collisions are infrequent but highly consequential. When they occur, they can significantly alter a planet's mass composition and rotation. Some planets gain additional layers of material, while others lose outer regions due to energetic stripping. These late impacts often define the final mass distribution of planets within a system. Rotation continues to evolve through these events. A single large impact can dramatically change a planet's spin rate or axis orientation. Because these collisions are directional and often off-center, they introduce significant angular momentum variations. Over time, the cumulative effect of multiple such events produces a wide diversity of rotational states. Some planets rotate rapidly, while others slow down, or even experience retrograde motion where rotation occurs opposite to orbital direction. The dissipation of gas also reduces the efficiency of angular momentum exchange between solid bodies and their environment. Without this medium, planets retain more of their acquired spin states. This means that rotational characteristics established during the late formation stages become more permanent, only slowly modified by later tidal interactions or additional impacts. Tidal forces begin to play a more prominent role once stable planetary systems are established. These forces arise from gravitational differences across a planet's structure, particularly in systems where planets are close to their host star or to large neighboring bodies. Over long timescales, tidal interactions can gradually alter rotation rates, often slowing planetary spin and synchronizing rotation with orbital motion in extreme cases. However, these changes occur slowly compared to earlier dynamical processes. Internal structure of planets also becomes more clearly defined during this stage. Differentiation processes initiated during earlier collisions continue to stabilize, producing layered interiors, consisting of metallic cores, silicate mantles, and in some cases volatile rich outer layers. These internal structures influence how angular momentum is distributed within each planet, affecting long-term rotational evolution. As the system matures, the remaining small bodies become increasingly isolated. Some are ejected into interstellar space through gravitational encounters, while others settle into distant reservoirs such as comet-like regions or scattered belts. These distant populations retain memory of the early chaotic environment, preserving traces of the system's formation history. The planetary system now transitions into a relatively stable configuration. Large-scale changes become rare, and most motion occurs on predictable orbital paths. However, subtle dynamical evolution continues, driven by residual interactions and slow energy exchanges between bodies. These processes operate over extremely long timescales, gradually refining the system's structure without fundamentally altering its overall architecture. Rotation of planets at this stage reflects a cumulative history of formation processes. Each spin state carries evidence of accretion patterns, collision history, internal differentiation, and gravitational interactions. The diversity of planetary rotation observed in mature systems is therefore not random, but the direct result of complex evolutionary pathways that unfolded during earlier stages of formation. By the end of this phase, the system has effectively moved from a gas-dominated environment to a gravitationally structured planetary arrangement. The motions of planets are now stable, but still slowly evolving under the influence of long-term gravitational and tidal effects. The differences in spin between planets are fully established, rooted in the unique sequence of events each body experienced during its formation within the original disk. In mature planetary systems, the dominant sources of motion arise from long-term gravitational interactions and the internal redistribution of energy within each planet. The surrounding environment is now largely cleared of gas, leaving behind stable orbits defined by the balance between a planet's inertia and the gravitational pull of its host star. Within this stable structure, each planet continues to evolve slowly, but its fundamental orbital and rotational characteristics are largely established. The diversity of spin observed across planets originates from the cumulative effects of earlier chaotic formation stages, now expressed in long-term stability rather than rapid change. The host star plays a central role in shaping rotational evolution through tidal interactions. Tides arise because the star's gravity exerts slightly different forces on the near and far sides of a planet. This difference creates internal deformation, producing friction within the planetary body. Over extremely long timescales, this friction converts rotational energy into heat, gradually altering the planet's spin rate. In many cases, this leads to rotational slowing, where planets take longer to complete a full rotation as energy is dissipated internally. Some planets approach a state of tidal locking where their rotation period becomes synchronized with their orbital period around the star. In this configuration, the same side of the planet always faces the star, while the opposite side remains in permanent darkness. This state does not occur quickly, but develops over billions of years in systems where tidal forces are strong enough. The transition towards synchronization reflects a gradual loss of rotational energy, rather than a sudden change. Internal structure strongly influences how planets respond to tidal forces. Planets with large molten or semi-molten interiors dissipate tidal energy more efficiently due to fluid motion within their layers. This enhances internal friction and accelerates rotational evolution. In contrast, more rigid bodies resist deformation, slowing the rate of spin change. The presence of oceans or thick atmospheres can also amplify tidal effects by redistributing energy across the planetary surface. Atmospheric dynamics introduce another layer of complexity in rotational behavior. Winds driven by solar heating and internal heat transport carry angular momentum across the planet's surface. These atmospheric flows can slightly speed up or slow down rotation, depending on how momentum is exchanged between atmosphere and solid surface. On some planets, atmospheric circulation patterns become so strong that they measurably influence the length of a day over time. The interaction between atmosphere and solid interior creates a coupled system where angular momentum is continuously exchanged. This exchange does not create or destroy rotation, but redistributes it between different layers. Over long timescales, this coupling can lead to gradual changes in rotational speed or slight shifts in the orientation of the rotation axis. Planetary cores play a key role in long-term rotational evolution. In many rocky planets, liquid metallic cores generate magnetic fields through dynamo processes driven by convective motion. These magnetic fields do not directly control rotation, but they are linked to internal heat flow and fluid movement, which are influenced by rotational dynamics. As a result, rotation and magnetic field generation become interconnected aspects of planetary evolution. Variations in axial tilt, also known as obliquity, emerge from earlier gravitational interactions and collisions. Once established, these tilts can remain stable or undergo slow oscillations depending on gravitational influences from neighboring bodies. Changes in axial tilt affect how a planet receives energy from its star, influencing climate patterns and long-term atmospheric behavior. However, these effects occur within a framework of already established rotational motion. Outer planets, particularly gas and ice giants, retain faster rotation rates due to their formation history. These planets accumulated large amounts of gas early in the formation process, preserving significant angular momentum. Their internal fluid structure allows for differential rotation where different latitudes spin at different speeds. This layered rotation reflects the dynamic nature of fluid interiors, where solid structure does not constrain motion in the same way as in rocky planets. Smaller rocky planets exhibit more rigid rotation profiles, though internal layering still allows for subtle differential motion between core and mantle. These differences accumulate over time, producing measurable variations in spin rate and orientation. Each planet thus reflects a unique combination of initial conditions and long-term evolutionary processes. Gravitational interactions between planets continue at a low level even in mature systems. These interactions can lead to slow orbital adjustments, slight variations in eccentricity, and long-term resonant relationships. While these changes are subtle, they can influence rotational behavior indirectly by altering tidal forces and orbital distances over time. The overall structure of the planetary system remains stable but not static. Small changes accumulate over millions and billions of years, gradually reshaping the details of motion without altering the fundamental architecture. Rotation, once established during formation, becomes a long-lived property shaped by both internal and external influences operating over vast timescales. By this stage, planetary spin is no longer a simple remnant of formation, but a dynamic equilibrium between tidal forces, atmospheric motion, internal structure, and residual gravitational interactions. Each planet carries within its rotation a layered history of its evolution, encoded in the subtle balance of forces that continue to act long after the disk from which it formed has disappeared. Within mature planetary interiors, motion continues in forms that are no longer visible at the surface, but remain essential to long-term rotational behavior. Beneath rocky crusts and thick atmospheres, internal layers of planets retain heat from their formation and from ongoing radioactive decay. This internal energy drives slow convection, where material moves upward and downward over vast timescales. Although these movements are extremely gradual, they play a critical role in redistributing angular momentum within planetary bodies. In rocky planets, the internal structure is typically divided into a metallic core, a silicate mantle, and a solid or semi-rigid crust. Each layer responds differently to stress and heat. The mantle, often partially plastic over geological time, behaves as a slowly flowing medium. This flow allows energy and momentum to be transferred between the core and the outer layers. The core itself may remain partially liquid, especially in planets with sufficient internal heat, enabling further fluid motion that contributes to long-term rotational evolution. The exchange of angular momentum between these internal layers is not uniform. Variations in temperature composition and viscosity create regions where motion is more active and regions where it is more resistant. Over time, this uneven distribution leads to subtle changes in the rotation rate of the planet. These changes are extremely slow, often measurable only over long observational periods, but they accumulate into meaningful differences in planetary spin behavior. In planets with active magnetic fields, the movement of electrically conductive fluids within the core generates electromagnetic forces. These forces interact with the motion of the fluid itself, creating feedback loops that influence both magnetic field strength and internal flow patterns. Although this process does not directly determine rotation, it is closely linked to the same internal motions that govern angular momentum distribution. As a result, magnetic activity and rotational evolution remain interconnected throughout a planet's lifetime. Atmospheric circulation continues to interact with surface rotation in complex ways. Heated by stellar radiation, atmospheres develop large-scale circulation cells that transport heat from equatorial regions toward the poles. These flows carry significant amounts of angular momentum which can be transferred between different latitudes and between atmosphere and surface. Over long periods, this transfer can slightly adjust the planet's rotation rate or modify the distribution of rotational speed across different regions. In gas giants, these atmospheric processes become even more pronounced. Without a solid surface to anchor, motion atmospheric bands extend deep into the planet's interior. Differential rotation emerges naturally with equatorial regions often rotating faster than higher latitudes. This pattern reflects the balance between internal heat flow, rapid rotation, and fluid dynamics within a deep gaseous envelope. The result is a highly dynamic rotational structure that persists over long time scales. Ice giants exhibit similar but more complex behavior due to differences in composition. Their interiors contain a mixture of icy compounds, rock and fluid layers under extreme pressure. These conditions produce unique convection patterns that influence both internal heat distribution and rotational behavior. Although their rotation is generally stable, subtle variations in internal flow can lead to small but measurable changes in spin dynamics. In all planetary types, tidal interactions continue to operate as a long-term influence. Even after the early formation period has ended, gravitational interactions with a host star or nearby large bodies can slowly alter rotation. These changes are cumulative and depend strongly on distance, mass distribution, and internal structure. Over extremely long timescales, they can lead to synchronization slowing or gradual reorientation of rotational axes. The orientation of a planet's spin axis remains a key feature of its long-term behavior. Axial tilt influences how tidal forces interact with the planet, how energy is distributed across its surface, and how internal stresses evolve. While major changes in axial tilt typically occur only during early formation, through collisions or strong gravitational perturbations, minor variations can persist throughout a planet's lifetime due to ongoing interactions. Residual bodies in the system, such as moons and smaller satellites, also contribute to rotational evolution. These bodies exert tidal forces on their parent planets, creating additional channels of angular momentum exchange. In some cases, this interaction leads to tidal locking between a planet and its largest moon, where both bodies always show the same face to each other. This configuration represents a stable equilibrium reached through long-term energy dissipation. The interaction between planetary rotation and orbital motion remains a fundamental aspect of system evolution. Rotation is not isolated from orbit, but is deeply connected through gravitational coupling. Changes in orbital distance or eccentricity can alter tidal strength, which in turn affects rotation. This interconnected system evolves slowly but continuously even after the main formation phase has ended. Over time, the cumulative effect of all these processes leads to a state of relative stability. Planets settle into long-lived rotational configurations shaped by their internal structure, atmospheric dynamics, and gravitational environment. However, this stability is not absolute. Subtle shifts continue to occur, reflecting the ongoing exchange of energy and momentum within and between celestial bodies. Each planet's spin is therefore a layered record of its entire history. From early accretion and violent collisions to slow tidal interactions and internal convection, every stage contributes to its final rotational state. The differences observed between planets are not random, but arise from the unique combination of processes experienced by each body during its formation and evolution. In this way, planetary rotation becomes a continuous expression of both past events and ongoing physical interactions. Even in the quietest stages of a system's life, motion persists in subtle forms, ensuring that no planet remains entirely static. Rotation endures as a fundamental property shaped by time structure and the persistent influence of gravity across every scale of planetary existence. Within the deep interior of planets, the slow circulation of material continues to influence rotational behavior in ways that unfold over immense spans of time. Heat trapped from planetary formation combined with ongoing radioactive decay of unstable elements maintains a persistent energy source that drives convection. This convection does not resemble rapid motion, but instead consists of extremely gradual movement of material within solid or semi-fluid layers. Over geological timescales, these slow flows become significant in shaping how angular momentum is distributed inside the planet. The core of a rocky planet, typically composed of iron and nickel, remains partially or fully molten depending on the planet's size and thermal history. In this liquid environment, convection currents form as hotter material rises and cooler material sinks. These movements generate complex flow patterns that are influenced by rotation. The Coriolis effect, a consequence of rotating reference frames, causes these flows to curve rather than move in straight lines. This curvature organizes internal motion into structured patterns aligned with the planet's spin axis. Above the core lies the mantle, a thick layer of silicate material that behaves as a very slow-moving solid. Over long periods, it can flow like a viscous fluid. This mantle flow is driven by heat escaping from the interior and by the sinking of denser materials. As mantle convection proceeds, it redistributes mass within the planet. Even small shifts in mass distribution can influence the planet's rotation by altering its moment of inertia, the measure of how mass is distributed relative to the axis of rotation. When mass moves closer to the rotation axis, the planet tends to spin slightly faster to conserve angular momentum. When mass shifts outward, rotation slows slightly. These changes are extremely gradual, but they accumulate over millions of years. This coupling between internal structure and rotation ensures that a planet's spin is never entirely independent of its internal dynamics. In planets with active tectonic systems, the movement of surface plates adds another layer of complexity. Lithospheric plates move slowly across the surface, driven by mantle convection beneath them. As plates shift, they redistribute mass across the planet's outer shell. Large-scale rearrangements of continental masses can subtly influence rotational balance, contributing to long-term changes in spin rate and axial orientation. Volcanic activity also plays a role in internal and surface coupling. As magma rises and erupts, it transfers material from the interior to the surface. Although the mass involved in individual eruptions is small relative to the planet, as a whole, repeated volcanic activity over long periods can contribute to gradual redistribution of mass. This process interacts with atmospheric and surface erosion cycles, further shaping the planet's rotational evolution. In contrast, planets without active tectonics experience more rigid internal behavior. Their crusts remain largely stable, limiting large-scale mass redistribution. However, even in these planets, slow cooling of the interior continues to affect density distribution. As the core gradually solidifies, latent heat is released, influencing internal convection patterns and contributing to long-term changes in rotation. Gas giants lacking a solid surface exhibit entirely different internal dynamics. Their interiors consist of thick layers of hydrogen and helium under extreme pressure. These layers transition gradually from gaseous to metallic states. Within this fluid environment, convection is intense and highly organized by rapid rotation. The result is banded atmospheric structures and deep internal flows that extend across vast distances. The rapid rotation of gas giants strengthens the Coriolis effect, leading to stable zonal winds that flow parallel to lines of latitude. These winds form alternating bands of eastward and westward motion. Although these patterns are visible in the atmosphere, they extend deep into the interior, indicating that rotation influences the entire planetary structure rather than just the surface. Ice giants show similar but more chemically complex behavior. Their interiors contain mixtures of water, ammonia, and methane under high pressure, forming exotic fluid layers. Convection within these layers is influenced by both temperature gradients and compositional differences. This leads to more irregular internal flow patterns compared to gas giants, though rotation still plays a dominant organizing role. Tidal interactions remain active in shaping internal dynamics, even at this stage of planetary evolution. The gravitational pull of a nearby star or large satellite can deform a planet slightly, generating internal friction. This friction converts orbital and rotational energy into heat, which is then distributed within the interior. Over long periods, this process can alter both internal structure and rotation rate. As energy is dissipated through tidal heating, it contributes to the gradual evolution of planetary interiors. In some cases, it can sustain geological or volcanic activity long after internal heat from formation has diminished. This ongoing energy input maintains internal motion, ensuring that rotational evolution continues even in older planetary systems. The coupling between atmosphere, surface, and interior becomes increasingly significant over time. Each layer of a planet exchanges energy and momentum with the others. Atmospheric winds transfer angular momentum to the surface, while internal flows redistribute mass and influence surface deformation. These interactions form a continuous system where rotation is maintained by dynamic equilibrium rather than static balance. Despite the complexity of these interactions, the overall trend in mature planets is toward gradual stabilization. Extreme variations in rotation become less likely as systems age, and most changes occur slowly over extended periods. However, stability does not mean immobility. Instead, it reflects a state where multiple competing processes balance each other, producing slow but continuous evolution. Every planet carries within its rotation the imprint of its internal structure and evolutionary history. From the deepest core to the outer atmosphere, motion is interconnected across scales. The spin of a planet is therefore not a simple inherited trait, but an ongoing expression of internal dynamics shaped continuously by heat gravity and the persistent redistribution of mass within its interior. Within mature planetary systems, rotation becomes a long-term expression of stability, shaped by slow and continuous exchanges of energy across internal and external boundaries. At this stage, the most violent processes of formation have long ended, but motion persists in subtle and deeply interconnected ways. Planets no longer grow through large-scale accretion, yet their spin continues to evolve under the influence of tidal forces, internal convection, and gravitational interactions with surrounding bodies. These influences act gradually, producing changes that unfold over millions or billions of years. The interaction between a planet and its host star remains one of the most important drivers of long-term rotational change. Even at great distances, the star's gravitational field exerts a continuous influence on planetary structure. This influence creates periodic deformation within the planet where material is slightly displaced from equilibrium positions. As the planet rotates, These deformations shift, creating internal friction that converts rotational energy into heat. This process slowly reduces rotational speed, although the rate of change depends strongly on distance, mass, and internal composition. In systems where planets orbit close to their stars, tidal effects become particularly strong. Over time, these planets may experience significant slowing of rotation, eventually reaching states where one hemisphere permanently faces the star. This condition, known as tidal locking, represents a stable equilibrium where rotational energy has been redistributed into internal heat and orbital motion. In this configuration, rotation still exists, but it is synchronized with orbital motion, creating a fixed orientation relative to the central star. Farther from the star, tidal effect weakens significantly. Planets in these regions retain more of their original rotational characteristics, preserving faster spin rates and more diverse axial orientations. These differences highlight how distance from the central star plays a key role in determining long-term rotational evolution. The same physical principles apply across all planets, but their outcomes vary depending on local conditions established during formation. Internal heat continues to drive slow motion within planetary interiors. Even billions of years after formation, radioactive decay of long-lived isotopes, such as uranium, thorium, and potassium, provides a steady energy source. This energy maintains convection within the mantle, and in some cases within partially molten cores. These internal flows continue to redistribute mass, subtly influencing rotation by altering the planet's moment of inertia. In planets with active magnetic fields, the movement of electrically conductive fluids within the core generates complex magnetic structures. These fields are not static, but evolve slowly over time as internal flows change. Although magnetic fields do not directly control rotation, they are intimately linked to the same internal processes that govern angular momentum distribution. Variations in magnetic field strength and structure often reflect deeper changes in internal motion. Atmospheric dynamics remain active even in mature planetary systems. Large-scale circulation patterns driven by stellar heating and internal energy transport continue to redistribute angular momentum across the planet's surface. These flows can slightly modify rotational speed and create measurable variations in day length. In some cases, seasonal or long-term atmospheric cycles produce oscillations in rotation that remain consistent over extended periods. Gas giants exhibit particularly complex rotational behavior due to their fluid structure. Without a solid surface, their outer layers can rotate at different speeds depending on latitude and depth. This differential rotation is maintained by deep internal convection and rapid planetary spin. The result is a layered rotational system where motion varies smoothly across different regions, rather than behaving as a single rigid body. Ice giants show similar but more irregular patterns due to compositional complexity. Their internal structure consists of multiple fluid layers with varying chemical composition, leading to uneven convection and less uniform rotational behavior. Despite this complexity, their overall rotation remains stable, shaped by the balance of internal heat flow and external gravitational forces. Smaller rocky planets, in contrast, tend to exhibit more rigid rotational behavior. Their solid surfaces limit large-scale internal redistribution of mass, resulting in more uniform spin characteristics. However, even these planets are not entirely rigid. Slow mantle convection and core dynamics still produce subtle long-term changes in rotation and axial orientation. Gravitational interactions between planets continue to influence rotational states even after system formation has stabilized. These interactions occur through long-range gravitational coupling, which can gradually modify orbital shapes and orientations. Changes in orbital configuration can in turn affect tidal forces, creating indirect pathways for rotational evolution. In systems with multiple large planets, resonant interactions can persist for extremely long periods. These resonances maintain specific ratios between orbital periods, creating stable but dynamic relationships. Although these configurations are stable, they still allow for slow exchanges of energy and momentum, influencing both orbital and rotational characteristics over time. The combined effect of all these processes is a gradual convergence toward equilibrium states. However, this equilibrium is not static but dynamic, maintained through continuous balance between competing forces. Rotation persists because energy is never fully removed from the system, but continuously redistributed among its components. Each planet's spin is therefore the result of layered influences operating across different scales. From deep internal convection to surface atmospheric motion and distant gravitational interactions, every layer contributes to the overall rotational state. These contributions accumulate over time, creating a complex and stable but evolving system. At this stage in planetary evolution, spin is no longer primarily a record of formation, but a reflection of ongoing interactions within a mature system. Although the most dramatic changes have long passed, the subtle processes that remain ensure that rotation continues to evolve slowly. Each planet maintains its unique rotational identity, shaped by a combination of ancient formation events and continuous physical processes operating across vast timescales. Within long-lived planetary systems, rotation enters a phase dominated by extremely gradual evolution, where changes unfold so slowly that they are measurable only across vast spans of time. The most energetic processes of formation have long ceased, yet the system remains active through weak but persistent exchanges of energy and momentum. These exchanges occur through gravitational interactions, tidal deformation, internal heat transport, and atmospheric circulation. Together they maintain a dynamic balance in which rotation is never fully static, even in seemingly stable worlds. Tidal interactions remain one of the most consistent long-term influences on planetary rotation. Even when a planet is far from its host, star-small tidal effects accumulate over time. These effects arise because gravitational fields vary slightly across a planet's diameter, creating internal stress. As the planet rotates, this stress shifts continuously, producing friction within internal layers. This friction converts rotational energy into heat, gradually reducing spin rate. The process is extremely slow, but continuous, ensuring that rotation evolves over billions of years. In closer orbits, tidal forces become significantly stronger, and their effects more pronounced. Planets in such environments experience strong deformation cycles as they rotate, leading to efficient energy dissipation. Over time, this can result in near-complete synchronization between rotation and orbital motion. However, even in these cases, small variations persist due to orbital eccentricity and internal structural complexity, preventing absolute uniformity. Internal structure plays a central role in determining how effectively tidal energy is dissipated. Planets with partially molten interiors respond more flexibly to tidal stress, allowing internal friction to generate heat more efficiently. In contrast, more rigid planets resist deformation, resulting in slower energy loss and longer timescales for rotational change. The distribution of materials within a planet therefore directly influences its long-term spin evolution. Deep within planetary interiors, convection continues to transport heat outward. This slow movement of material redistributes mass over geological timescales, altering the planet's moment of inertia. Even minor shifts in mass distribution can affect rotation, as conservation of angular momentum requires adjustments in spin rate. These changes are subtle but continuous, ensuring that no planetary rotation remains entirely constant. In some planets, particularly those with active geological or volcanic systems, surface and interior coupling becomes more complex. Material is transported between deep layers and the surface through volcanic activity and crustal recycling. These processes contribute to slow but persistent redistribution of mass. Over long periods, they can slightly modify rotational characteristics, especially when large-scale surface restructuring occurs. Atmospheric dynamics continue to influence rotation in planets with substantial gaseous envelopes. Large-scale wind systems transport angular momentum across different latitudes, creating slight variations in rotational speed between equatorial and polar regions. These differences are not static but evolve with changing atmospheric conditions driven by seasonal cycles or long-term climate variations. In some cases, these atmospheric motions can even influence the length of a planetary day in measurable ways. Gas giants exhibit particularly strong atmospheric coupling due to their deep fluid envelopes. Their rapid rotation enhances the organization of atmospheric bands, creating stable jet streams that persist over long periods. These jets are not isolated surface features, but extend deep into the planet's interior, linking atmospheric motion with internal convection. This deep coupling ensures that rotation is distributed across multiple layers, rather than confined to a single rigid structure. Ice giants, with their more complex internal chemistry, show more irregular coupling between layers. Differences in composition and phase transitions within their interiors lead to variable flow patterns. These variations influence both heat transport and angular momentum distribution, resulting in subtle but continuous changes in rotational behavior. In rocky planets, atmospheric influence is more limited but still present. Dense atmospheres can transfer angular momentum between surface and atmosphere, creating small but measurable effects on rotation. Over long periods, these interactions contribute to variations in spin rate and axial stability. Even without strong internal fluid layers, surface processes remain connected to rotational evolution. Gravitational interactions between planets introduce additional long-term complexity. These interactions are weak individually but persistent over time. They can cause gradual changes in orbital shape and orientation, which in turn influence tidal forces and rotational behavior. In systems with multiple large planets, these effects can combine to produce intricate patterns of long-term, dynamical evolution. Resonant orbital relationships can stabilize planetary configurations over extended periods. In these cases, gravitational interactions lock planets into repeating cycles that maintain consistent orbital ratios. While stable, these resonances still allow for slow energy exchange, which can subtly influence rotation and orbital structure over time. This creates a system that is both stable and continuously evolving. Magnetic fields remain an indirect but important factor in rotational evolution. Generated by internal fluid motion, these fields reflect the same convection processes that influence angular momentum distribution. Changes in magnetic field structure often correspond to shifts in internal flow patterns, which can in turn affect rotational dynamics. Although the connection is indirect, it highlights the deep coupling between different planetary systems. Over extremely long timescales, planetary systems approach a state of near equilibrium, where large-scale changes become increasingly rare. However, equilibrium in this context does not mean complete stillness. Instead, it describes a balance of continuous but offsetting processes. Energy is constantly exchanged, but overall structure remains stable. Rotation persists within this equilibrium as a long-term outcome of initial conditions modified by ongoing processes. Each planet's spin reflects not only its formation history, but also billions of years of gradual adjustment. The result is a stable but evolving system where rotation continues to carry the imprint of both ancient events and present-day interactions. At this stage, planetary spin is fully integrated into the broader dynamics of the system. It is no longer a separate property, but part of a continuous interplay between internal structure, orbital motion, and external gravitational influences. The diversity of spin observed across planets is maintained not by randomness, but by the complex and ongoing balance of forces that operate across multiple scales of time and space. Within ancient planetary systems, the passage of time reveals rotation as a deeply persistent but slowly evolving property shaped by countless subtle influences. The most dramatic formative events have long ended, yet the system remains active through low-level exchanges of energy that continue without interruption. These exchanges occur through tidal interactions, internal convection, atmospheric circulation, and gravitational coupling between bodies. Each process contributes in small increments to the gradual evolution of rotational states, ensuring that no planet remains completely unchanged over astronomical timescales. Tidal forces continue to act as one of the most reliable mechanisms for long-term rotational change. Even when their immediate effects are weak, their cumulative influence becomes significant over billions of years. As a planet rotates, gravitational differences across its structure produce internal deformation. This deformation generates friction, which slowly dissipates rotational energy as heat. The process does not require external variation to persist. It is maintained by the constant relative motion between planetary rotation and external gravitational fields. In systems where planets orbit close to their host, star-tidal evolution progresses more rapidly. Rotation gradually slows as energy is transferred from spin into heat and orbital motion. Over time, this can lead to synchronization between rotation and orbit, although the process is rarely perfect. Residual orbital eccentricity and internal structural variations ensure that small deviations persist, preventing complete uniformity. Even in synchronized systems, subtle oscillations in rotation remain present due to ongoing gravitational interactions. Inside planets, internal heat continues to drive slow but continuous motion. This heat originates from both residual formation energy and long-lived radioactive decay. As heat rises from deeper layers, it drives convection within the mantle, and in some cases within fluid cores. These convective motions redistribute mass within the planet, altering its internal structure and moment of inertia. Because angular momentum must be conserved, even small changes in mass distribution can produce measurable effects on rotational speed over long time scales. The relationship between internal structure and rotation becomes particularly important in planets with partially molten interiors. In these bodies, fluid motion allows for efficient redistribution of angular momentum. As materials circulate within the interior, they transport energy and mass in complex patterns shaped by temperature gradients and rotational forces. This continuous movement ensures that rotation is not isolated from internal dynamics, but remains closely linked to the planet's evolving structure. On the surface, geological processes continue to contribute to slow rotational change. Tectonic activity where present moves large sections of a planet's crust over time. These movements redistribute mass across the surface, subtly affecting rotational balance. Even in planets with limited tectonic activity, processes such as erosion and sedimentation and volcanic resurfacing gradually shift mass distribution. Although these effects are small individually, they accumulate across geological timescales. Atmospheric systems also play a role in shaping rotational behavior. In planets with substantial atmospheres, large-scale circulation patterns transport heat and angular momentum across the surface. These flows are driven by differences in solar heating and internal heat flux. As air moves between regions, it exchanges momentum with the surface, producing slight variations in rotational speed. Over long periods, these interactions can influence the overall length of a planetary day. In gas giants, atmospheric motion becomes deeply integrated with internal structure. Strong jet streams and banded circulation patterns extend into the planet's interior, linking surface motion with deep fluid dynamics. Rapid rotation enhances the organization of these flows, creating stable but dynamic structures that persist over long timescales. The result is a highly layered rotational system where different regions rotate at slightly different speeds. Ice giants exhibit more complex internal behavior due to variations in composition and phase transitions within their interiors. These differences create uneven convection patterns, which influence both heat transport and angular momentum distribution. Although their rotation remains broadly stable, small variations in internal flow produce subtle changes in rotational dynamics over time. Gravitational interactions between planets continue to influence rotational states even in mature systems. These interactions are typically weak but persistent, gradually altering orbital parameters and indirectly rotational behavior. Changes in orbital eccentricity or inclination can modify tidal forces, which in turn affect rotation. This indirect coupling ensures that planetary spin remains connected to the broader architecture of the system. Resonant orbital relationships can persist for extremely long periods, maintaining stable ratios between planetary orbits. These resonances create structured gravitational interactions that repeat regularly over time. While they contribute to system stability, they also allow for slow energy exchange between bodies. This exchange can influence both orbital and rotational evolution, maintaining subtle dynamical activity within otherwise stable systems. Magnetic fields continue to reflect internal planetary dynamics. Generated by fluid motion within conductive layers, these fields evolve slowly as internal conditions change. Although magnetic fields do not directly control rotation, they serve as indicators of internal flow patterns that influence angular momentum distribution. Variations in magnetic structure often correspond to changes occurring deep within the planet's interior. Over vast timescales, planetary systems approach a state of long-term equilibrium in which large-scale structural changes become rare. However, this equilibrium is not static but dynamic, maintained by continuous but balanced processes. Energy flows persist, but they do so in a way that preserves overall system structure. Rotation exists within this balance as both a stable and evolving property. Each planet's spin represents the accumulated outcome of its entire history, from initial formation within a rotating disk to billions of years of subsequent interaction and adjustment. No single process determines rotational state. Instead, it emerges from the combination of internal structure, external forces, and long-term gravitational relationships. This layered history ensures that every planetary spin is unique, reflecting the specific conditions under which it formed and evolved. In this mature stage of system evolution, rotation is fully integrated into the broader dynamics of celestial motion. It is neither independent nor isolated, but continuously shaped by interactions across multiple scales. The diversity of planetary spin observed across systems is therefore not accidental, but the natural result of persistent interconnected physical processes operating over immense spans of time. Within ancient and stable planetary systems, rotation continues as a quiet but persistent expression of long-term physical balance. The most energetic phases of planetary formation have long faded, yet motion remains embedded in every layer of each planet. Even in systems that appear calm and unchanging, subtle exchanges of energy continue to shape rotational behavior. These changes are not abrupt or visible on short timescales, but they accumulate gradually, revealing the deep continuity of physical processes that govern planetary evolution. Tidal interactions remain active across the system, acting as one of the primary drivers of slow rotational change. As a planet and its host star exert gravitational influence on each other, internal deformation occurs repeatedly with each rotation. This deformation generates friction within planetary materials, converting rotational energy into heat. Over time, this process steadily reduces rotational speed, though the rate depends on distance composition and internal structure. Even in distant or weakly affected planets, the effect persists at extremely low levels, ensuring that no rotation remains entirely unchanged. In closer planetary orbits, tidal effects become more pronounced. Planets in these regions experience stronger gravitational gradients, leading to more significant internal deformation. This accelerates rotational evolution, sometimes resulting in long-term synchronization between rotation and orbital motion. However, even in these cases, perfect stability is never fully achieved. Small variations in orbital shape and internal structure introduce minor fluctuations that preserve subtle dynamical motion. Deep within planets, internal heat continues to drive slow convection across multiple layers. This heat originates from both residual energy from formation and ongoing radioactive decay. As heat moves outward, it generates internal circulation patterns that redistribute mass. These movements alter the planet's moment of inertia, causing slight adjustments in rotational speed. The conservation of angular momentum ensures that even minor shifts in internal structure produce corresponding changes in rotation, maintaining a continuous link between interior dynamics and spin. In rocky planets, mantle convection remains one of the most important long-term processes influencing rotation. The mantle behaves as a slowly flowing solid over geological time, allowing material to circulate in response to heat gradients. This circulation redistributes mass across the planet's interior, subtly affecting its rotational balance. In some cases, large-scale mantle upwelling or downwelling can contribute to measurable long-term changes in spin behavior. The core of a planet, often composed of iron-rich material, also plays a central role in rotational evolution. In many planets, the core remains partially liquid, allowing fluid motion that interacts with planetary rotation. This motion can generate magnetic fields through dynamo processes which are sustained by convection within the conductive fluid. Although magnetic fields do not directly control rotation, they are closely linked to the same internal movements that influence angular momentum distribution. At the surface, geological processes continue to operate slowly but steadily. Tectonic motion, where present, shifts large sections of crust across the planetary surface. These movements redistribute mass over long timescales, subtly altering rotational characteristics. Even in planets without active plate tectonics, surface reshaping through erosion, sediment deposition, and volcanic activity contributes to gradual changes in mass distribution. Atmospheric circulation adds another layer of complexity to rotational dynamics. In planets with substantial atmospheres, large-scale wind systems transport energy and angular momentum across different regions. These flows are driven by uneven heating from the host star and internal heat sources. As atmospheric currents interact with the planetary surface, they exchange momentum, producing small but persistent changes in rotation rate. Over long periods, these interactions can slightly lengthen or shorten the length of a planetary day. Gas giants exhibit especially dynamic atmospheric behavior due to their deep fluid structures. Without a solid surface boundary, atmospheric and internal flows are deeply interconnected. Strong jet streams extend into the planet's interior, creating a continuous system of differential rotation. Different latitudes and depths rotate at slightly different speeds, producing a complex layered rotational structure that remains stable over long time scales. Ice giants, with their mixed composition of gases, ices, and rock under extreme pressure, show more irregular internal dynamics. Variations in composition lead to complex convection patterns that influence both heat transport and rotational behavior. Although their overall spin remains stable, small fluctuations in internal flow create subtle variations in rotational dynamics over time. Gravitational interactions between planets continue to shape rotational states even in mature systems. These interactions are weak individually but persistent over long durations. They modify orbital shapes and orientations, which in turn influence tidal forces and rotational evolution. In systems with multiple large planets, these interactions can create long-term resonant relationships that stabilize orbital motion while still allowing slow energy exchange. Resonances between orbital periods maintain structured relationships that persist over immense timescales. While these configurations provide stability, they also permit subtle dynamical evolution. Energy and momentum can be exchanged gradually between planets, influencing both orbital and rotational properties. This ensures that even stable systems remain dynamically active at a low level. Magnetic fields continue to reflect the internal state of planets. Generated by fluid motion within conductive regions, these fields evolve slowly as internal conditions change. Although they do not directly determine rotation, they serve as indicators of deeper processes that influence angular momentum distribution. Changes in magnetic structure often correspond to shifts in internal convection patterns. Over time, planetary systems approach a form of equilibrium in which large-scale changes become rare but not entirely absent. This equilibrium is maintained by a balance of continuous processes that offset one another. Rotation persists within this balance as a stable yet evolving property shaped by both ancient formation events and ongoing physical interactions. Each planet's rotation at this stage represents a fully developed expression of its history. It reflects the combined influence of formation within a rotating disk, early violent collisions, long-term tidal interactions, and internal structural evolution. No single factor dominates. Instead, rotation emerges from the accumulated effects of many processes acting across different scales and timescales. In this mature phase of planetary evolution, spin becomes a stable but dynamic characteristic of each world. It is maintained through continuous interaction between internal structure, external gravitational forces, and long-term energy redistribution. The diversity of planetary rotation observed across systems is therefore the natural outcome of complex and layered physical processes operating consistently throughout the lifetime of a planetary system. In the most mature stages of planetary systems, rotation exists as a long-term equilibrium shaped by countless layers of physical interaction. The system has reached a state where large-scale formation processes have ceased, yet motion continues in subtle, continuous ways. Planets orbit in stable paths around their host star while internal and external forces maintain a slow but persistent evolution of rotational states. This stage represents not an end of activity but a refinement of earlier chaos into long-term stability governed by balance rather than disruption. Tidal interactions remain one of the most enduring influences on planetary rotation. Even in systems that have existed for billions of years, gravitational gradients between a planet and its host star continue to generate internal deformation. This deformation produces friction within planetary materials, converting rotational energy into heat. Over extremely long timescales, this process gradually reduces rotation rates or stabilizes them into synchronized states. The effect is strongest in close orbits, but even distant planets experience it in weakened form, ensuring that no rotational state remains completely unchanged indefinitely. Internal heat continues to drive slow convection within planetary interiors. This heat originates from residual formation energy and ongoing radioactive decay, both of which persist over geological time. As heat moves through the interior, it creates circulation patterns within mantle and core regions. These flows redistribute mass within the planet, subtly altering its moment of inertia. Because angular momentum must be conserved, even small internal shifts produce corresponding adjustments in rotation. This ensures that internal structure and spin remain deeply connected throughout a planet's lifetime. In rocky planets, mantle dynamics play a central role in long-term rotational evolution. The mantle behaves as a slowly deforming solid over vast timescales, allowing convection to transport material across large regions of the interior. This movement redistributes density, which can slightly accelerate or decelerate rotation depending on how mass shifts relative to the axis of spin. Although these changes are extremely gradual, they accumulate steadily, preserving a continuous link between geological activity and rotational behavior. The planetary core contributes further complexity to this system. In many planets, the core remains partially liquid, allowing fluid motion that interacts with rotation through Coriolis forces. This motion can generate magnetic fields through dynamo action, where the movement of conductive fluid produces self-sustaining electromagnetic structures. While magnetic fields do not directly control rotation, they reflect the internal flow patterns that govern angular momentum distribution. Changes in magnetic structure often indicate deeper adjustments in rotational dynamics occurring within the core. At the surface, geological and atmospheric processes continue to influence rotation in subtle but persistent ways. Tectonic movement shifts large sections of crust over long periods, redistributing mass across the planetary surface. This redistribution alters the planet's rotational balance slightly, contributing to slow variations in spin. In planets with active surface geology, volcanic resurfacing and erosion further modify mass distribution, reinforcing this gradual evolution. Atmospheric systems also contribute to rotational behavior. Large-scale wind patterns transfer angular momentum across the planet's surface, driven by uneven heating from stellar radiation and internal energy sources. As these winds interact with the surface, they exchange momentum, producing small but measurable changes in rotation over long periods. In planets with dense atmospheres, these effects can become particularly significant, creating variations in the length of a day over time. Gas giants exhibit especially complex rotational structures due to their fluid nature. Without a solid surface, their atmospheres and interiors form a continuous system of motion. Differential rotation arises naturally, with equatorial regions often rotating faster than higher latitudes. This layered rotation extends deep into the interior, reflecting the interplay between rapid spin convection and fluid dynamics. Despite this complexity, the overall structure remains stable over long timescales. Ice giants display similarly layered but more irregular internal behavior. Their composition includes mixtures of volatile compounds under extreme pressure, creating multiple interacting fluid layers. These layers generate complex convection patterns that influence both heat transport and rotational dynamics. Although their rotation remains stable, subtle variations in internal flow create long-term fluctuations in spin characteristics. Gravitational interactions between planets continue to operate at a low level in mature systems. These interactions modify orbital parameters slowly, which in turn affects tidal forces and rotational evolution. In systems with multiple large planets, long-term resonant relationships can persist, maintaining structured orbital patterns while allowing gradual energy exchange. This ensures that even stable systems retain a degree of dynamical evolution. Magnetic fields remain visible expressions of internal planetary dynamics. Generated by fluid motion in conductive regions, these fields evolve slowly as internal conditions change. While they do not directly determine rotation, they serve as indicators of the processes that do. Variations in magnetic structure often correspond to shifts in internal convection, which influence angular momentum distribution and long-term rotational behavior. Over vast timescales, planetary systems approach a state of dynamic equilibrium. In this state, large-scale changes become rare, but motion does not cease. Instead, it becomes balanced across multiple interacting processes that continuously exchange energy and momentum. Rotation persists as part of this equilibrium, neither fixed nor chaotic, but maintained through ongoing physical interactions. Each planet's spin is the result of a complete evolutionary history, beginning with formation in a rotating cloud of gas and dust, and continuing through billions of years of interaction, collision, and gradual adjustment. The final rotational state reflects this entire sequence of events encoded in the balance between internal structure, external forces, and long-term gravitational relationships. In the end, planetary rotation is not a simple property but a living record of physical history. It carries the imprint of formation, transformation, and long-term stability. Every variation in spin, every tilt, and every change in speed reflects the cumulative effect of processes operating across immense scales of time and space. Even in the quietest and most stable systems, rotation continues as a subtle expression of the universe's ongoing physical order.